In this video, we're going to go over some notes for section 3.6, implicit differentiation. Super important that we have watched this and kind of given ourselves a chance to go through it prior to class on Tuesday. I would say my advice would be to pause the video for a couple minutes and work through A through D here on your own. It's just a little bit of differentiation review, chain rule for all of these. Hopefully shouldn't take you too long, so pause that, work through those. Alright, I'll assume that you have paused and worked through those, and so I'll just go ahead and work through it quickly then and see, hopefully my work matches with yours. Again, hopefully we recognize right away that all of these are fairly straightforward chain rule, just one part of chain rule, not two or three parts, and then there's no quotient rule or product rule in there as well. That's what I mean by straightforward. Okay, so start with the inside part, that's u. U equals x squared equals outside part y equals sine of u. Take the derivative of each of those, writing it in our fraction, our Leibniz notation is 2x dy du is equal to cosine of u. Multiply those together and substitute back in, and we get dy dx is equal to cosine of 2x, oops, sorry, not cosine of 2x, cosine of x squared times 2x. I'm going to do C, which is right underneath that next, because I see the pattern here of, well, this one's also dealing with a sine. So the difference here between these two is the outside is the same. It's a sine of something, but then we've changed what u represents. So as we go through this one, u is different. U is now 4 to the x. Hopefully you watched the video last week about the derivative of a to the x, not just e to the x, but any number a to the x. So then du dx, dx equals natural log of 4 times 4 to the x. And then this part, y equals sine of u, dy du is equal to cosine of u, that's all the same. So I'm not going to write that again. I'm just say, hey, do this again. And then we'll just put it together. Dy dx is equal to cosine of u, but now cosine of u is now 4 to the x, times natural log of 4 times 4 to the x. So because the outside part was the same, sine and sine, all that changed, in both cases, the outside is sine, the derivative of that is cosine, and so what changes in my derivative is, well, what's the u that I plug back in inside of that, and what's the du dx that I multiply by at the end. We'll notice the same pattern over here. The outside is the same, it's just a square root function, and then the inside what's different. Here it's cotangent of x, here it's this binomial. But again, we can walk through this here. So here, I'm going to do my work up top actually, some nice white space here. U is equal to cotangent of x. So the derivative of that, if we remember our rules, it's a cofunction, so it's got a negative, and then it's cotangent x. Mixing up my cotangent and my secant. It is, whoa, what's happening? Here we go. Negative cosecant squared of x. And now the outside, as we said, is going to be just the square root, which we know we should just write as to the 1/2 power. So if that's y, then I now need dy du to be 1/2 u to the negative 1/2. Now I'm ready to just multiply those two things together and substitute back in for u to get my dy dx. dy dx is 1/2 u to the negative 1/2 times negative cosecant squared of x. I didn't really do a good job organizing my work up here. Usually I try to follow a pattern like u and then du underneath it, y and then dy underneath it, or maybe they're both next to each other. Here it's just kind of this weird clump, which I don't like. But either way, we do the same thing. Now, I left this as a u. I need to go back and substitute in u. A mistake I was noticing people making last week is plugging in du here. And that's why I think the notation is so crucial. Call that inside part u, call its derivative du dx. Don't call it u prime, call it du dx. Call this outside part y, and don't say it's x to the 1/2, say it's u to the 1/2. And then the derivative is dy du, because it's always the instantaneous rate of change of the output variable with respect to the input variable. So then last step, substitute in here. So this is now 1/2 of cotangent x to the negative 1/2 negative times negative cosecant squared x. And of course that could be cleaned up and simplified quite a bit, but I'm going to skip that because it's not our focus for right now. Same thing in this next one. We notice again, hey, there's this pattern that I still have something inside this square root. So the derivative of the y, the outside part, is going to be the same. It's just the inside part and thus the derivative of the inside part which have changed. So I'm again going to save a little time here and just work with the inside part. So u in this case is 3x to the 4th minus 2x cubed. So du dx is 12x cubed minus 6x squared. Now, using this same derivative of the square root chunk that we had before, I know that I'm going to just end up plugging in the same stuff. So I'm really going to have the exact same format here. It's going to be, because I'm going to still have this 1/2 u to the negative 1/2, but I'm just changing what I plugged into that and changing what the derivative that I multiply at the end is. So my derivative should be 1/2. Now u to the negative 1/2, yes, but this time u is 3x to the 4th minus 2x cubed to the negative 1/2. And then instead of multiplying by negative cosecant squared, I multiply by 12x cubed minus 6x squared. And this is all of this, noticing this pattern. I noticed some people last week picking up on some of these patterns and saying, oh, well, I've done this type before, I can use this again as a shortcut. That's great, but more than that, we want to be able to use, we're using these patterns to establish the idea of implicit differentiation, which is our section for today and in class on Tuesday. So when I notice here sine of q, y equals sine of q, I'm noticing, hey, this is sine of something, sine of something. So the derivative here, I don't know what this q is, but just like here I have u standing for two different things. So when I write sine of u here, that's implied, it is implicit, not explicit, that this u stands for something else. And I will then, in the end, need to multiply by its derivative. This u stands for something else, and I will in the end have to multiply by its derivative. So as we look at this one, I'm going to say that the derivative here, dy dx, because that's what the directions ask me to find, dy dx, is the derivative of the outside, which the derivative of sine is cosine, plug the inside back in, right? Leave it as cosine of u, and then here I was able to actually plug in the function for that because I knew what the function was. It was explicitly stated to me that u is equal to x squared. Here, it's not explicitly told to me what q is, but is implied that it stands for something. And so when I explicitly knew what u stood for, I could find its derivative and multiply by that. But now it's only implied that q is some other function and thus has a derivative. But I still need to multiply by its derivative. I just don't know what that derivative is. So all I can write is times dq dx. And that is the answer. Now, we used to say you can't leave this u we can't leave this u in the answer. We can't leave a u as part of our answer. We had to substitute back in for x. So what's the deal with this q? Well, I would like to get rid of it. I would like to substitute something in there for it. But I don't know what q stands for. It's implied that it stands for something, but I don't know what. So I just have to leave it as a q. Same thing over here. My t, what is that t? I don't know, but it's implied that it stands for something. So dy dx is equal to 1/2 t to the negative 1/2 times dt dx. The variables are so important because they could have asked me in this question to find dy dq. And then I wouldn't need this extra thing because then it's no longer implied that q stands for something. They've told me, oh, find the rate of change with respect to q, where q is the input variable. So if they had said find dy dq, I would say, all right, no problem, it's cosine of q. I don't have to multiply by anything out here anymore because now that you've told me q is the input variable, you're no longer implying q is only a dummy variable for something else. Which up top, when they say find dy dx, that's telling me y is the output, x is the input. Anything else is only a dummy or placeholder variable and can't be part of my final answer. So it's so important in this section and going forward that we pay attention to the variables. Now, what letter is it? There's not meaning in, oh, this time they used Q and this time they used T and this time they used U. No, none of that matters. But how the variables relate to one another is so important. So over here we say, well, why did you switch to a T? That doesn't matter. But what does matter is that they asked me to find dy dx, and there's a t here. So that means that's implying to me that this is just a placeholder variable for something else, so I must multiply it by its derivative here. Now, something else that's important to hit on here is that, well, another way to look at these expressions is I've actually taken the derivative of this y and then multiply and said, okay, well, y stands for some function, just like t stands for some function, and I have to then multiply by that unknown derivative. Y stands for some unknown function. And what's the derivative of any variable by itself? Well, it's 1. And then multiply by its unknown derivative, the implied function here. It's implied that y stands for something, so multiply by its derivative, just like with chain rule. Same over here. I could say this y is implying to me that it stands for some function. So take its derivative and do chain rule. Oops. Do chain rule. Stop that. Sorry, I'm too close to my menu bar and it keeps grabbing tools that I don't want it to grab. So what chain rule says is take the derivative of the outside, multiply by the derivative of the inside. Right? Take the derivative of the sine, multiply by the derivative of the 4 to the x. So we could also say we'll take the derivative of the y, that's just 1, multiply by the derivative of the function that stands for, which we just call dy dx. Again, I keep emphasizing the word implied because the title of the section, the title of this method is implicit differentiation. Now, when we use implicit differentiation, it's for a certain type of equation. It's for, oops, wrong way. It's for an equation that looks like this. Now, I've provided the graph for us here for two reasons. One we'll get to in a minute, but the first is notice that this is not a function. For some of our inputs, for an input of 3, we have 1, 2, 3 outputs. 1 input, 3 outputs. Failing the vertical line test, not a function. So the graph here helps me see that. Now, when I look at this equation, and the directions again say find dy dx, y is the output variable, x is the input variable. If one option, something that we did in one of the homeworks, was we just said, okay, well, I need one variable by itself to be able to do this. So I can try to, because y is told to me as the output variable, I can try to solve this for y. However, that's not algebraically possible. There's just no way you can do it. Feel free to pause the video and try for a minute if you want. I think Mr. Shields is wrong. I can solve that. Well, you can't. You can't get one y all by itself. It's just not going to work. So I have to take the derivative like this. And so what I do is I just go through and I take the derivative, sum and difference rule, take the derivative of each term individually, including the other side of the equation. This other side happens to be 0, but I could make it, 100 if I want. Let's do that. Let's make it 100, make it more interesting. Okay, so we're going to take the derivative of each term individually. So the derivative of x cubed is, of course, 3x squared. The derivative of y cubed is 3y squared. But, hold on, here's where implicit differentiation happens. Y is not my input variable. So it is implied, because it's not my input variable, which I know this one on the bottom has to be my input variable, this is something else. So it is implied, just like my Q and my T on the other page, this has to be standing for something else. I don't know what it is, but it's got to be standing for something else. So then that means I have to multiply by dy dx. Now, wait a second. Why didn't I multiply by dy dx after this first term? Because this is x. That's my input variable. It's not implied that it's a placeholder for something else. This is a different variable, so it is implied that that it stands for something else, some other function, some hidden chain rule here. So I have to multiply by the derivative of that inside part, whatever it might be, even though it's hidden from me right now. Now the next term, super fun, this is a product. Now to make that product less terrible, because technically you have three things multiplied together, negative 9, x, and y, I'm going to group the negative 9 and the x. You could group the negative 9 and the y, but why change the order if you don't need to? Oops, we were writing in red there. So we're going to say minus 9x, I'm going to leave that first term alone, times the derivative of the y. Well, the derivative of the y is 1, and then implied chain rule times dy dx. Then plus, now the derivative of negative 9x is negative 9 times leave the y. No dy dx here. Why no dy dx here? Because I didn't take the derivative of the y. I took the derivative of the x, just like over here. I took the derivative of an x, no dy dx. Now on the other side, equals the derivative of 100, which the derivative of any constant is 0. And now we do have a little bit of algebra to do here. The directions say find dy dx. So that means they actually want one dy dx by itself on one side of the equation, no other dy dx's. So we got to do a little solving. First thing to do there, if you want to go ahead and pause and see if you can solve it for yourself, that'd be a great idea. But here's how I'll do it. Anything that doesn't have a dy dx with it, I'm going to send to the other side. Anything with a dy dx, I'm going to keep over here. So 3y squared dy dx minus 9x dy dx equals 9y minus 3x squared. And now I have these two separate dy dx's, and they're certainly not like terms. So what I can do is I can factor that out. Say dy dx times 3y squared minus 9x equals 9y minus 3x squared. Dy dx then, to get it by itself, I need to divide, is 9y minus 3x squared over 3y squared minus 9x. You could factor out a 3 from everything if you wanted to, that'd be fine, but not required. Now I said in the beginning it was important to notice that we had both x's and y's in this equation. And notice now we have both x's and y's in our derivative. And that's important. The reason that is important is, like we said before, we have a relationship here that is not a function. So if you said, what's the slope at x equals 3, well, how do I know which slope you're talking about? You're talking about this one, or this one. Those appear to be three different slopes, two positive slopes and one negative slope. So how do I know which one you're talking about? Well, the only way I know is if you give me not only an x, but also a y value to plug in. And then I can find the slope at a particular point using both the x and the y. So in class on Tuesday, we'll go deeper into this idea of implicit differentiation. We'll practice it. And you should have a couple practice problems assigned for your Monday homework as well to follow up from this video.